Thank you very much for coming along tonight. I believe we have some guests tonight. Welcome. I hope you enjoy yourselves. Tonight I'd like to welcome Cassidy Mihalenko and introduce her to the group here tonight, who's going to be talking to us about some of her work. Cassidy is actually a member of the ASV, which we won't hold against her. One of those minor little clubs around the place.
Just a couple people.
Yeah. And Cassidy completed her degree in physics at the University of Melbourne recently and has done a master's, and she's here as a doctoral candidate working with Carell, who spoke to us one night last year.
Almost a year ago, yeah.
Cassidy's going to be talking to us about astronomical transients. The real ones, not the ones that are chemically induced as you lie down on the grass in the backyard and stare up at the night sky. So, I've never experienced that. So, once again, Cassidy, welcome, and please proceed.
Thank you. Oh, thank you very much for the introduction and for the invitation to come and talk here. It's really amazing to get to meet all of you, and hopefully I'll get to talk to you all after the presentation. So like Mark said, my supervisor, Carell, has been here to give you a talk before, and I also know other people from the optical group at Utas have been to give talks previously, such as Tom Plunkett, who I work with, as well as Andrew Cole and whatnot. So because I know you've had talks from these people before, when I was planning this, I was trying to figure out how do I give you a talk that you haven't heard before? How do I make this a bit different? Especially with Carell, we work quite closely together, so there's a lot of overlap in what we're studying. So I decided that because I did my master's at Melbourne in a slightly different topic than what I study now, that today that we were just going to take a step back, and instead of talking about my sort of niche little area of science, we're all just going to go through a tour of the universe on the transients that are in our universe, and why I think that they are really interesting, and why I think everyone should care about them, even if you haven't necessarily heard about them all yet. Can I have a Would it be easier to get a clicker or something? I don't know. There's going to be a lot of clicking.
Did you want to? I can't get it to move. There we go.
Wonderful. Thank you so much. All right. So transients. Before we dive into that, I mean, I think the definition of the word is going to give away a lot of the stick of what I'm talking about here. But I do need to put in a caveat that in the astronomical community, like the science community, the definition of transient is quite strict. Today, what I'm going to talk to you about here is going to be much more broad, because I don't want to narrow myself down in what we can talk about. There are a bunch of interesting things that are sort of in related areas and tangential to that. So if I can have another clip, please. There's going to be lots of this. Or we can just have this beautiful image.
I'm so sorry, Cassidy.
Oh gosh, all good. Yeah, okay, so it's going to be much clicking, so if we good? Okay, yeah, so the definition that I'm working with here is just anything that changes its brightness over time, and I have here short time scales, astronomically short time scales. So the things that we'll talk about today can be anything from hours to days, weeks, a couple months, but kind of at the most a year or so in the kind of events that I'm interested in here. And to prove to you before we even start why I think that this is a really interesting topic, I do have my next slide. Hopefully everything plays right. Or I don't have my next slide.
No, you don't have it. I don't know what I'm doing now. No, that's...
Oh, that's it.
There we go.
I've got to get them at the cursor over there.
So this is my summary slide of why transients are an interesting thing to talk about today. All of the things on the screen here are different kinds of astrophysical transients. I get to talk about stars that explode, stars that collide, black holes ripping stars apart, galaxies, planets, all of these things get subsumed into the category of transients. There's a huge field and full of most fascinating things, violent, energetic, explosive. So I think I have the coolest job in the world, that I get to spend all day, every day thinking about all of these different kinds of things. Okay.
Sorry, Cassidy, Lisa's just got the biggest.
That's okay, she wanted to see my really amazing intro slides.
See, I set that up just to get the applause. That's what you don't know.
All right, so my last slide was showing you some really cool things, but they were all artist impressions. It's what it would look like if we could go out into space and actually see them, but can't do that, unfortunately. So this is much more like what we're actually going to be looking at in the science context. So we've got our bright event, and it's been running for too long, so it pauses itself. We had our light curve here, so brightness over time, and we can watch it evolve.
Oh, come on.
Beautiful. Okay, so I promised you a tour, so we're going to do this in stages, and we're going to start our journey through the universe with our galactic transients. So this is anything that is nearby to us. It could be within the Milky Way or in one of like our local group, perhaps Magellanic Clouds. But these are all events that we're only really capable of seeing close to us. That was 2. Beautiful. All right, so our first group of transients that we're going to start with are variable stars. So for many people who are aware, most stars are pretty well constant over the time periods that I'm talking about of years, right? The sun's 4.5 billion years old or something to that effect, right? So we do have some interesting stars, such as this one here that you can see, where they actually change over timescales of days. Here we're looking at about 40 days or so of a star changing its brightness over time. And there are 2 main reasons why this could happen. We've got our extrinsic, so something outside the star, so perhaps like a dust cloud or something. The other one is intrinsic, which is the star itself is changing its brightness over time. Next slide, please. Beautiful. So the first case, extrinsic, an example of that would be something like this. This is an eclipsing binary, so we've got 2 stars orbiting each other. And if the plane of their rotation is in our line of sight, so we're looking at them edge on, we can see one passing in front of the other. And that's naturally going to mean it's blocking each other's light as they go past each other. So we're going to see our light curve having dips in brightness over time. So these ones are usually pretty periodic, but it is something that's changing over a short time scale, so it gets included in my journey today. Please. All right. For an intrinsic case, we could have something like this, a pulsating or a periodic variable star. Cepheid variables are Lyrae. These are stars that are having some sort of mass instability. So as they sort of condense, we're crushing the core, we're upping temperatures, we're upping energy production, pushes back against gravity, everything drops. You kind of get this cyclic motion. So we're seeing this periodic behavior. And if we're looking for other kinds of transients, these are really important to know and understand, especially in catalogs, because when I'm going out and I'm looking for something new going off in the sky and I'm just seeing the start of this rise, I want to know whether it's one of these or if it's the sort of event that I'm looking for, which happens to not be these. So they're important to know in the context of transients. Getting a bit closer to the sort of things I'm interested in, here we have an example of a novae, a nova, novae being plural. So a lot of us will be familiar with the term supernova. The nova instead is where the star that undergoes the explosion actually survives the process. So an example here is we have a white dwarf in the middle here, and we've got a companion star whose material is being pulled off itself onto the smaller star. Creates an instability because they're really sensitive about their weight. So yep, here we have an example of if that wants to play. It does want to play, fabulous. This guy here. We're seeing that in the April, we've got a nice bright object. A year later, it's gone back to its regular brightness. So it still exists as a star after undergoing that extreme event. Some of these can be cyclic, some of them aren't, but it is an explosive, interesting event. And just to give you an example of one that might be more familiar with, not too long ago, Betelgeuse was making itself known in a lot of news and astronomical discussion cycles because of its dimming event, its unprecedented amount of dimming. This is believed to primarily likely be because a dust cloud or something extrinsic, because you can also see a bit of a change in the shape. But just as a nice recent example of a star that you can see by eye, whose variability was also visible by eye, the amount of change in its brightness. Right. Stop 2 on our galactic transients is microlensing events. So those of you who would have happened to have seen Tom Plunkett's talk would probably have heard about these guys because that's his area of work, but we're going to stop in on them anyway. Next slide, please. So microlensing is a consequence of space-time. So we know that light travels in straight lines, and we also know that when there is a curvature in space-time, that will cause the light to bend. So we see as our object passes through, we're seeing a double up of the event because the light is being bent around both sides. But what this does is it actually acts like a magnifying glass. So we've got our source at the back, our lens in the middle, and the amount of light we're getting from the source is increased due to the lens passing in front of it. So we can use this to see objects that are fainter that we wouldn't normally be able to see when we have the perfect lineup of an object passing in front of it. So to qualify, when I'm saying things like gravity and stars and stuff, there's probably more just regular lensing than micro-lensing. But we have an example here of what this might actually look like. So our star passes in front, we're getting our light curve. But as the planet passes in front, you're seeing an extra little bump there in the light curve. And that is super interesting because we can use our theoretical models and our computational models to actually use the light from the background source star to understand the properties of the planet. By fitting models, we can look at its size, its mass, its distance from its host star. So we can study an object who doesn't emit light itself by looking at the object behind it. And further consequences of lensing in general is we can use that to study galaxies. If the galaxy is the lens, or even galaxy clusters, it's a way of measuring dark matter. But it's a really interesting event from the effect of relativity and perfect lining up of some events to our line of sight. All right, that's a really quick go through of our galactic because that's not my field. So we're going to spend a little bit more time here on the next leg of our tour, moving further away, moving out to extragalactic transients. So the first one that I want to talk about here are fast radio bursts. So fast radio bursts, as the name suggests, are fast bursts of radio light. They are incredibly energetic, so they have about 80 years worth of sun's energy being emitted in just milliseconds. Really, really quick events. Some of them repeat, some of them don't. Get my next slide, please. This here is an example of what fast radio burst looks like in actual radio data. So this one here is the first fast radio burst ever observed. That was only observed in 2007. This area is really, really current, really new, and as I have in my dot point over there, still a complete mystery. We don't know what makes these. Don't know why they repeat. We don't know why they don't repeat. This is a current area of research, but really interesting in Australian science because this guy was actually observed by the Parkes Radio Telescope. Yeah, and the man who led a lot of the exploration of fast radio bursts, Professor Matthew Bales, who works at Swinburne, just last year won the Shaw Prize for this work. So keep your eye out on these guys because there are a lot of people interested in trying to figure them out. Next up is something called a tidal disruption event. So I think these are pretty cool and likely one that less people have heard of. So a tidal disruption event is when a star gets ripped apart by a black hole. I think it's very cool. So tidal, again, being gravitational, so our own tides or tidally locked moon, other things like that. If a star passes close enough to a black hole, but not so close that it falls in, it's going to go within a certain radius and it gets stretched and stretched until the star can't hold itself together anymore and it gets ripped apart. So you get the material from the star, some of it's going to get flung off into space, and some of it's going to end up on a orbit that will fall back into the black hole, and it'll round and round and round it'll go, and it'll accrete back onto the black hole. And when it forms into that accretion disk and starts interacting with itself, it creates a really bright flare. Next, please. This is kind of what it's going to look like. And because it's accreting so quickly, we actually get the formation of some relativistic jets of material coming out. Not all TDs will create jets, but some of them do. But you're seeing you're getting some unbound material, some falling in, and some of these streams are hitting into each other. So you're getting material hitting into itself, creating even more energy. So these guys can be really, really bright events. And these are really cool because they actually allow us to study the black hole. So if we can understand the color evolution, does it jet, does it not, a bunch of these properties can be modeled to understand properties of the black hole. What's its mass, what's its spin, all of these other kinds of properties. So again, a really cool way to use an explosive or transient event to study something that doesn't emit light in itself. Top 3, one of my favorites, we are finally going to hit onto our supernovae. So, supernovae, the deaths of massive stars. Now, stars like the sun will not undergo a supernovae, but once you get to somewhere around 8 times the mass of the sun and above, the star will become unstable in the end of its life and undergo an explosion. These guys are incredibly bright. One supernovae can be as bright or brighter than its entire galaxy. So we do have 2 types of supernovae. Most of them are going to be core collapse. So this is sort of what we're familiar with when we're thinking of the death of the star. It burns through all of its fuel in its core, hits to iron where it can no longer undergo fusion, and so it's going to suffer a collapse and then an explosion, like what you were seeing here. Can we go next one, please? But we do have a second type, so type 1a. So supernovae are classified into types 1 and 2 and then subtypes from there based on their properties. So what elements are in them, what does their color evolution look like and whatnot. But type 1a's are unique because they are the one kind that are not core collapse. So these guys, as you can see in the animation, we've got a neutron star and a companion star. And the companion is feeding material onto the neutron star, kind of similar to the novae, but different, white dwarf versus a neutron star here. And neutron stars are also very sensitive about their weight, but very sensitive. Anything above about the mass of, I think it's 1.4 solar masses, and they freak out and they explode, which is what gives us this explosion here. So neutron stars are really fascinating, and we're going to talk a little bit more about them later, but they are incredibly dense, made up entirely of neutrons. So if you imagine taking the sun and squishing it all the way down to the size of a city, about 30 kilometers across, that's the kind of densities that we're talking about. And these guys are really interesting because it's the same physical process that creates all of them. It's a neutron star accreting material above its mass limit. And so they all explode exactly the same way with pretty much exactly the same brightness. That's a fantastic tool for distances. It is really hard to measure distances in space. Things are very far away. If they're close to us, we can kind of measure how they move relative to background. We're going to talk about parallax. But these guys we can see in galaxies much, much further away. And we know exactly how bright it is. So if we know how bright it is and then we know how bright we observe it to be, we can calculate the difference and calculate a distance measure. Really fantastic. All right. So as I mentioned, neutron stars, we're going to discuss how we get there. So these are the result paths. So this diagram here is telling us about stellar evolution. This top path being what our sun will undergo. Most stars will just have a pretty boring lifetime. They'll swell up and then they'll just leave a dead core. But for our most massive stars, we get to have some fun at the end here. So this is how we create the neutron stars, as I was mentioning before. Those stars that are massive enough to undergo a supernovae, but not the most massive, when they undergo that implosion, it will condense their core into neutrons. So it's condensing it so much that our protons and our neutrons get, protons and our electrons, excuse me, get squished in together to create neutrons. Hence why it's called a neutron star. Really dense object. But if it is a particularly massive star, it's going to crush straight past that, push everything down into a singularity, and that's how we're getting to our stellar mass black holes. And we also get our lovely nebulae left over as our stellar supernova remnants, which are always beautiful to observe. And these guys I think are particularly interesting. We're talking about incredibly dense objects with some crazy physics going on with them. So watching supernovae, seeing how they evolve into these different things, the types of elements that they produce, really, really fascinating events. So now that we've spoken about our neutron stars and our black holes, those are what we call compact objects. We can make our next stop at compact object mergers. So we can have any combination of those three, black hole, neutron star, or two neutron stars. This animation here is showing us about gravitational waves. Everything that we've talked about so far is we're talking about light and using light to study the universe. But when we have compact objects, their gravity is so intense that if you have a pair of them, as they rotate around each other, they'll slowly lose energy to gravitational waves. And they move further and further in, they rotate, they in spiral until we hit to a merger. And you can see that as they get closer and closer together, the amount of the amplitude of gravitational wave increases. So gravitational waves were observed for the first time in 2015, which is very exciting because it provides us an entirely new way of observing the universe, completely distinct from light, which means that we have access to new information that we couldn't see before. And so this is obviously an ongoing field, very cool detectors, very fun stuff happening there. Next, please. And now, after everything that we've set up, next stop is to gamma ray bursts. So this is getting towards what I actually study in my own PhDs. There'll be a little bit more detail in these slides. So before I tell you how we make them, I just kind of want to show you what a gamma ray burst is. Again, name is quite obvious, a burst of gamma rays. We like nice naming conventions. But essentially it is this part here that I'm talking about. So as I said, I'll explain how we make it, but essentially you end up with a black hole in the middle, but you get these really focused jets coming out of the event of gamma rays, and that's what we observe. So you only can see a gamma ray burst if you're looking down the jet. So if I'm an observer from underneath, I'm not going to observe this particular gamma ray burst. I have to be over here looking down the jet angle. So it makes them a little bit harder to see because you need them pointing at us. So we've got our prompt emission, so that's just our high energy gamma rays, but as they move out into space, that high energy particles are going to interact with the surrounding medium, and we get this emission across every other wavelength of light, all the different colors, and that's a component that we call an afterglow. So with these events, we'll see the gamma ray burst first, and then as that system evolves, we'll be able to see the afterglow traveling through all of the different colors of light. So for me, as an optical observer, I'm looking for the afterglows to these events because I can see the optical component. So now that we kind of know what it is, we're looking at that jet, we're looking at these incredibly high energy events. They break up into two different categories. We have, based on their duration, the amount of time for which we see the gamma rays. So we have our longs and our shorts divided by about 2 seconds. And they, we believe, are created by two different progenitors. Two different things make the longs and the shorts. So the longs here, pretty similar process to what we've discussed because we think that they're, well, we're quite confident that they are related to supernovae. So one particular kind of supernova, it's called type 1bc, just tells us you about the kind of star that happens. But we think that that kind of supernovae creates a gamma ray burst that takes about 2 seconds or more. But I'm more interested in the shorts because these guys are created by compact object mergers, and particularly those of two neutron stars. There are some theories that we might be able to see them from a neutron star and a black hole merger. We haven't seen it. We don't have observational evidence of that yet, but we do know that they are linked to two neutron star mergers. But what I'd like to point out about this is despite the different mechanism, you can see that this final component here, they look the same because it is the same physical process creating the gamma ray burst component, creating that jet. Just got some animations just to kind of show the point. So we've got our supernovae, we've got our collapse, we've got our jet breakouts for our longs. And next, please. And then we have our short scenario where we've got a neutron star merger. All right, so that's our quick introduction to gamma ray bursts. But now we're going to talk about kilonovae. So these are related to a few of the things that we've just spoken about. And we'll come back to these a little bit later on in the talk because they're of my interest. So a kilonova is related to a binary neutron star merger as well. So these guys are related to our gamma ray bursts, or at least our short gamma ray bursts. Remember how I said our gamma ray bursts, we can only see them when we're looking down that jet? But in the diagram that I showed much earlier, we had our jets and then we had that little like really pale blue ball that I was like, ignore that, I'll talk about that later. That's what I'm talking about now. So when you get two neutron stars colliding, as well as creating that accretion onto the black hole in those jets, we also just get a kind of ball of neutron-dense material that gets tossed out as part of the process of that merger. And so we can kind of see them here. And when you have all of those neutrons thrown out into this really hot, intense environment, they start creating all of the heavy elements of the universe, pretty much the whole bottom part of the periodic table. And a lot of that is radioactive. Radioactive elements are unstable, and so as they decay, they emit light. And so the light that we observe from that radioactive process is specifically the kilonova. So it is that component of the merger. So we've got our merger, we've got our gamma ray burst, we've got our kilonova, each coming together as a total part of this entire process. Excuse me. So yeah, why they might be interesting to just the everyday person is that these are the places in the universe where gold, platinum, uranium, they're created by these neutron star mergers. So if you own any gold, stellar collisions, that's why they're fun. So supernovae do create some of the heavy elements, especially like closer to iron, but we realized a while ago that while supernovae create some of the heavy elements, they didn't create enough to populate the universe as we saw. So we have now discovered that kilonovae are responsible for the vast majority of the very heavy elements in the universe, which is great for us on Earth because oxygen and carbon count as heavy elements to us astronomers. Next, please. All right, so the first two legs of our tour of the universe have taken us through different kinds of astronomical transients at all different kind of stages, different energies, different places in the universe. And that's all well and good because I've shown you a lot of really nice pictures and animations, but is that what they really look like? How do we actually see them? So the next part of our tour is how do we actually observe these? How do we see them? Step one is some luck. Transients are not guaranteed. They're transient. You don't know when they're going to happen. You don't know where they're going to happen. You kind of just have to, at some point, be a little bit lucky that you're looking at the right place at the right time. So to just give you a bit of summary, for supernovae, we're kind of expecting roughly one per galaxy every 50 to 150 years, depending on your estimates. There have been about 8 visible by the naked eye throughout history. Here, 2 lovely examples. Stellar remnant, supernova remnant, supernova. GRBs, we can see about 1 per day, but that's with gamma ray burst satellites in space, looking at the sky all of the time, doing our best to catch as many as we can. Variable stars, there's only 10, maybe 20 or so that you can actually see with the naked eye, varying in brightness. So the answer is we need some really good setup to be able to actually find these guys and do some science. So how to do that? Step 1 is, well, step 2, that's step 1 in the process, search and survey. So if we want to be seeing more of these guys, quick answer is just look at a lot of the sky and look at it for a really long time, right? So we want to be looking at a large volume of the universe to increase the number of galaxies we're looking at, to increase the number of events that we might be able to see happen within them. So we want wide field, we want to cover a really large portion of the sky. And here we've got an example of, these are a bunch of different surveys that are doing this work. So these are mostly acronyms. But these are just showing you the region of sky that they are covering when they are taking images. So for example, we've got our little moon here, but DES has taken a fairly big region. LSST is going to do a nice big one. ZTF, huge region of the night sky. Because these guys are just staring at the sky, waiting for something to happen. And they usually come back every couple days, couple nights. And next step is difference imaging. So when you were looking at the sky every couple of nights, you build up a nice catalog of what things looked like before anything happened. And so as you can see, we have this image here is a reference image, what it looked like before. This image here is our science image, which has our event in it. I don't know about you, but if I looked at those two, I probably wouldn't pick out a difference. But we can use subtraction, so taking one image from the other to identify that there is something new in this image. And you can tell it's a good subtraction because all of these other little guys have vanished out nicely. It looks like background. It's nice check for ourselves mentally that everything's working the way it should. And so we can see that we've got an event there. So we're doing our large surveys and we're comparing constant images to previous images, looking for when something goes off, hoping to catch it as early as possible. So here's just a list of few of the observatories that are doing this, and I wanted to put up a picture for each, but then I figured we'd be here for ages as I tried to list all of the cool ones. So just a really quick summary is we're going to go from gamma rays all the way in the highest energy. We've got SWIFT, we've got Fermi, we've got SVOM. These are all different space satellites that are looking for gamma rays and some X-rays. Ultraviolet, we've got SWIFT. So while it is a gamma ray detector, it's designed such that if it sees a burst, it'll switch its camera over to ultraviolet to see if it can find an afterglow. Optical, I could not be bothered trying to list everything that people are doing. People all around the world and in space are, or using space-based observatories, trying to find new things going off in the sky, including us here in Tasmania, like where everyone's trying to just watch for new things. Infrared, James Webb Telescope is a nice recent one. It's in the news a lot. It's got some fantastic images. our infrared, which is really, really nice because that was a bit lacking in some of our observatories. Radio, I've listed 2 Australian ones, Parkes, familiar to most people. Australia Square Kilometre Array Pathfinder, or ASCAP, much easier to say. Australia pulls our weight in radio. We do a ton of work. We have really fantastic radio observatories, and these guys are always looking for new events. And for example, our fast radio bursts, they're doing a pretty good job. And of course, our gravitational waves. So the next step is that, okay, you've got your really big sky surveys, you're watching the sky all the time, you're looking for when something new goes off. When we see one go off, what do you do then? That's when we switch over to follow-up. Please. What we do is we receive our alerts, and this screenshot here is an example of an online website that I use called Astronomy to, they just collate a whole bunch of alerts. Anytime anyone sees something, they share it, gives us all the nice information, where it is, how bright it is, what colors, all of that good stuff. We get our alerts. I say, okay, here's all of the new stuff going off in the sky. I check where it is, and if it's observable from my sky, I just get on the sky. Get your telescopes, get on it, and chase it as much as you can. So the people who are doing their large sky surveys, because they're looking at so much all the time, they're usually coming back to fields maybe once a night. A lot of them are probably going to be every couple of nights. They don't have the capabilities to, when they see something, really nail down and narrow in on it and track it. So that's where the follow-up is important. You get smaller observatories that are dedicated to those things, where they just say, this guy looks interesting, let's go look at it and look at it in detail, get a lot of data on it. Please. So the next leg in our tour is bringing it all the way back to local. I can tell you about all the amazing satellites, all the amazing telescopes all around the world, but I moved down to Tasmania to do this work, so why would I do that if I didn't think it was something cool that we could do down here? First one should be one that many people are familiar with, Mount Pleasant Observatory. Not really used for transients, so probably not the best for this conversation, but it's a fantastic facility, and I think it's a gorgeous looking telescope, so I had to mention it. But we are talking to a lot of the radio people at Utas and trying to figure out if and how we can start doing some collaborations with these guys. But this is where I'm much more comfy. So the Greenhill Observatory up at Bisty Tier, this is the facility that I use for the most part of my PhD. It is why I moved down to Tasmania. A lot of telescopes, or a lot of large science telescopes, in order to get time on them, you need to apply, you need to get approved, you only get a little bit of time, you've got to hope that the sky is clear for the days you got approved for. All a great process, and I have been through some of that. But here with our Greenhill Observatory, we're the only ones using it, which means I and the other people in my optical group get uninterrupted access to this facility. To our 2 telescopes, we've got a 1.3 meter and our 0.5 meter telescope, and that's just invaluable that I can jump on sky any night that it's clear, any night that I want, to try and hunt down any of my transients. And my last point here is a unique view of the southern sky. There aren't a ton of optical telescopes in Australia, but the fact that we're in Tasmania so far south is such a huge advantage to us. There's obviously tons of observatories in the northern hemisphere, and there's quite a few over in Chile. But when you get to Tasmania, where we're on the other side of the world and south, we have such a unique part of the sky that we can cover from here. It makes us invaluable when we want to collect data. When other telescopes go to daytime and they can't see these events, we can fill in key parts of the light curve with our data. So it makes us pretty valuable to people that want to collaborate with us. So just a quick overview of which of our transients that we met tonight that we're doing work on with our observatory. So again, microlensing, I mentioned Tom before. The other ones are all my field of research. So supernovae, gamma ray bursts, and kilonovae with an asterisk because I'm hunting for them. I haven't seen one yet, but I am trying my best. Hopefully we'll get to see one with our facility. This place. Right, so as I said, just to give you a little bit of a taste of my own personal research, since we've done such a really broad overview, essentially my PhD can be narrowed down to the question of how do we find more kilonovae? I'm gonna try my best. So this is sort of similar to the image I mentioned before. Here is our jet and our afterglow from our gamma ray burst, and then our nice little red kilonova down there. And so I say it's in red there because it glows most in red optical light and infrared, where we're most likely to find it. Next, please. Okay, so I told you what a kilonova is, but I would have to tell you about 170817, so gamma ray burst and gravitational wave, 170817, so that's just the date, 17th of August 2017. This was the first kilonova ever seen. 2017, not that long ago, so this is a pretty new field of research. So we saw a gravitational wave and a gamma ray burst coincident with each other at the same time in the same place in the sky. People all around the world have gone, oh my God, it's going to happen. Everyone's got on the sky. We've had more than 70 telescopes on the ground and in space, all chasing this alert, wanting to see this. Because I told you before that we thought short gamma ray bursts and neutron star mergers were linked. Until this, that was just theory. This is the event that proved that link existed. And so this is our little guy up there, nice and red. You can see him fading over time. These events are quite quick. Kilonova is going to be seen a couple hours to a day after the gamma ray burst, and then it's gone. So it's not easy to find. But we found the afterglow, we found the kilonova. So it's fantastic, so exciting. Our techniques are working, transients is all making sense, except we didn't really see another one. So all of our theory kind of predicted we were going to see maybe 2 or 3 a year. 2017 is a while ago, and this is the only really confident one we've got. So something's up. This is where my PhD has come in. So, slide please. We do have, so that's our one really confident one. We do have a handful of other ones that we think are probably kilonova, but they're not quite what we expected. For example, we've seen 2 that were linked to long gamma ray bursts, but we were pretty sure that long gamma ray bursts were linked to supernova, so it can't have a kilonova because that needs a neutron star. So we're kind of getting ourselves a little bit stuck of, we're seeing things, but not quite how we expected to see them. We don't really know. There's maybe some others that might be a little bit more red than we thought. How do we find them? Like, we're not confident. So that's what I want to try to do. Now, observing is the reason why I got into astronomy. I want to use telescopes. I want to look at all these really cool explosions in the night sky. So that's the main part of my reason for wanting to do a PhD. So that's why it's up there as the first point of why, of what I'm trying to do here. So what we're doing is we're using our Greenhill Observatory to follow up with GRB alerts when we get them, if they're in our sky. Jump on sky with our telescope, see if we can find an afterglow. Let's add to some data, do what we can. But I'm also trying to think of how can we do this better? Other people are out there doing follow-up, but it's not worked yet. We haven't found another one. So I'm trying to think, what can we do? How do we better maximize our use of small facilities, whether, 0.5 meter, 1.3 meter, not huge telescopes, but how can we make them work better for us? But also, what other techniques can there be? Can we be focusing on particular types of gamma ray bursts? Can we be focusing on the types of galaxies that we're looking at? So I'm trying to investigate a lot of those features. But while I wait for the kilonova, and I'm sure that we're going to find one, I'm also doing a bit of a search in past data. So as I mentioned, we saw some maybe kilonova events we didn't expect to see them. So I'm also going to do a bit of a comb through some archival data and see if maybe there's a kilonova there, but we missed it because we didn't know what we were looking for. So now I'll just give you a quick summary of our observing, because let's be real, that's the fun bit, and that's the nice pictures. GRB follow-up. We've been doing what we can, but we don't have a ton of nice pictures. We have one we're working on right now, but that's in progress, so I don't have a nice picture to show for you yet, which is kind of annoying. So we'll skip on to the fun transients, please. Beautiful supernova, we love it. So the image that was added to my event description on the AST website was of supernova 2024 GGI. This is my own version of those pictures. So this image here is not mine. This is just taken from archival data online of that location. And this here is an image in R band, so essentially red, taken with the 50 centimeter telescope. Look at that beautiful bright supernova. Not quite as fun as the artist impressions that I showed you before, I know, but we have some bright pixels and I found that very exciting. So this particular event is interesting because it was one of the closest supernovae to happen to us in somewhere around 20 years or something like that. So it was incredibly bright, and people around the world got some really nice data when filled in the light curve. And our Tasmanian observations, go to the next slide, please. Got our light curve, so we've got our different colors, red, green, and more red, sort of. But essentially we can see that we've got our nice rise and our nice decay. So we've seen some really important parts of our light curve. We've seen that peak. And I'm collaborating with someone at the University of Melbourne with some of their data and their collaborators And our data was really nicely placed to help fill in some of the data points of their light curve. So hopefully that work will come out soon. And I don't have fun pictures of this yet because I tried to find them, but I didn't find any great ones. We are working with some other collaborations as well to increase our likelihood of seeing something. It's not just us with our, 1 or 2 telescopes trying to explore the entire world of transients. We're working with other people around the world. So we're collaborating with the SVOM collaboration. So I mentioned in an earlier slide, SVOM was one of my gamma ray burst satellites. We're working with them. They're giving us alerts, and we're working with other people on ground to follow up their transients. I also mentioned DWF there, so that stands for Deeper, Wider, Faster. So that's a collaboration I'm working on with a group at Swinburne who are doing that survey approach, just staring at the sky with about 10 different telescopes in different wavelengths at once, seeing what kind of transients we can just spot. They've managed to see supernovae and novae, variable stars, GRBs, all kinds of fun things just by staring at the sky, but they're doing it in all different colors of light, all at exactly the same time. So some really interesting light curves because we're not getting that trigger and follow-up. We're getting multiple things all at once. Really interesting. So I have spoken at you at some length about all the kinds of transients, well, not all, but a good summary of the kinds of transients that we see in the night sky at all kinds of different timescales and different distances, how we're supposed to see them, why we care about them, and why I care about them. So I just want to leave you with a little bit of tour highlights, which is that there's all kinds of fun stuff going on out in the universe all the time. If you care about stars or planets or galaxies or black holes, there's always something cool happening out there if you're just happy to go out and look for it. And that all of us are part of that. So Carell has mentioned when they gave their talk to you as well that amateur astronomers are often seeing things. They're often seeing supernovae and contributing to citizen science. So all of us observers are part of trying to understand what's going on in the universe because you never know who's going to be looking at the right part of the sky at the right time. And that Tasmania is important. We have such a fantastic sky. We've got a nice southern sky. We've got nice clear skies. We've got a beautiful view of the Milky Way galaxy, better than pretty much anywhere else in the world. So we should absolutely be making sure we're enjoying our sky. And this is my last slide, but I kind of just like to think of, as someone who has studied supernovae, gamma ray bursts, and kilonovae, all of these crazy, violent, explosive events. But these are the places in the universe where we have to thank for life, for oxygen and carbon and all of these kinds of things. And without them, without the violence in them, we wouldn't be here. So I think it's really cool that we get to then go back and study them and see how they work. But yeah, thank you for coming with me through the universe. So, yeah, of course. Yeah.
Earlier you talked, Cassidy, about you had no, that's dangerous. No, this will never end. No, just a quick question. You had a binary system where you had, I think, a red giant, or I'm not sure what the companion star was. And you had a white dwarf. You were talking about novae and the accretion of material onto the disk. What physical processes prevent that star from exceeding the Chandrasekhar limit, and actually, why is that different from a binary system where you've got a type 1b supernova where one accretes all the material and then explodes and ejects the other stuff, and what's left of the other stuff?
So I'm more familiar with the type 1a supernovae, just the nova itself. Take what I say with a grain of salt, because it's not my field of research, so I should check that before I really answer that for you. My understanding is the nova, the small companion, is a white dwarf star, so a dead stellar core. Whereas the type 1a supernova is a neutron star. So the neutron star is subject to the Chandrasekhar limit, and it's very highly sensitive to its change in mass. The nova, I think, is just a smaller scale explosion, so I don't think it compresses all the way through to the core, but I'm not super familiar with the physics of the nova, so I can check that for you.
Yeah, I wondered what was happening to that material. So it gets burned, it gets combusted off. There's a flash point, but there's no. Then it goes back to it goes through the cycle again.
Yeah.
I was wondering why it wouldn't go beyond that and accrete material to the point where you do get the other type of supernova where you get the star exceeds that limit of 1.4 solar masses and goes bang.
Yeah, so that would just end up in a type of event. So the nova is just when it is small scale, it's on the surface and it's just having those small scale explosions, it's not disrupting the star. But if you had a constant accretion that did disrupt the entire star, that would not be a nova because that would be a larger scale event.
So it's just that combusting event that
the small scale, I think, and I'm not entirely sure what physical process it is that triggers it to have small scale explosions instead of constant.
Yeah,
Um,
yeah.
But I can try and look that up and answer that for you later.
Yeah, thank you. Thanks. Oops.
Yeah, I took a photo of the SN2024 GGI, and I followed that for about 3 months. It was still exploding 3 months later. And about a month after that, there was nothing there. So that one only lasted 3 months. But there was a report recently, there was a 2013 supernova that suddenly has reignited. So is that even possible?
I'm not familiar with this particular event. A supernova shouldn't be a cyclic thing, so my initial instinct might be it could have been a core collapse that created a neutron star. So we have that one supernova that creates that compact remnant, and then if you had a companion accreting onto that, you then get a type 1a. So that would be my initial guess as to how you could get two supernovae happening in the same system, because they would be separate events, but supernovae in and of themselves are not repeat events.
I had the coordinates of it as well, so I took a photo of it, and it was only as big as a pixel because it's 183 million light years away.
Yeah.
It's the furthest object I've ever photographed.
I mean, that's pretty impressive to be able to photograph just with any facility.
Okay. It was a long time ago when they started looking at gamma ray bursts and trying to find optical transients. There was this idea that there should be a prompt optical flash corresponding to a gamma ray burst. People started looking, doing all sky cameras and looking for transients there. Now, I can't remember ever seeing anybody that found optical at the same time as a gamma ray burst.
Yeah, to my knowledge, it hasn't been observed. A lot of that struggle comes from the fact that gamma ray bursts, being as energetic as they are, we can see them much further away than we're able to see any optical component. So, I mean, that makes it difficult enough to find an afterglow. So the odds of finding a gamma ray burst close enough for us to see the optical and to have a gamma ray facility and an optical facility looking at the same patch of the sky at the same time, it's just a really difficult thing to do. So people are absolutely still trying to do it, and that lines up with what the Deeper, Wider, Faster program we're trying to do by having multiple colored facilities on sky at the same time. But yeah, to my knowledge, we haven't yet got there. Yeah. Yeah. Just unfortunately, yeah, the optical light is much fainter, so we can't see as deep, which means we just can't see as many of them. Just a challenge of working in transients. Like I said, there's a lot of luck involved.
Cassidy, I'm just wondering whether in the work that you're doing in Tasmania here, whether you have access to the gravitational wave data from anywhere around the world, or?
So some amounts of that are public, I believe. I'm not a part of the collaboration, but my supervisor is or was. I don't know if they've renewed that, but I am a member of, should flag this symbol here is for AusGrav. So I am a member of the Centre of Excellence in Australia for Gravitational Wave Research. So the Centre of Excellence is just for any who doesn't know, a body or a region, a portion of research question that the government deems really important to do research, and they fund it quite heavily. So the government is currently funding gravitational wave research in Australia, and I'm a member with them. So even though I don't think I have direct access myself, I have access through partnerships. But I'm an optical person, so to me, I would work in collaboration with gravitational wave people. It's not stuff that I've worked on myself very much.
Okay, thank you.
Questions? There's one online. You'll have to read it out, Matt.
Justin Young wants to know, as a citizen scientist, is there a way to support the research by going through data released to the public, similar to research taking place through data for exoplanets?
Yes, so my understanding is there is not currently one for kilonovae or GRB afterglows, just because we don't see the sheer volume of those to release out to the public, because a lot of the times those citizen science things are we have so much data that we just need more eyes. So I don't believe we have any for gamma ray bursts or kilonovae, but it's a conversation that I've actually just recently been having with some, not collaborators, but people I know who are doing it for TESS data. So TESS is a satellite looking for exoplanets, but they are trying to do some citizen science stuff using data from that satellite, but looking for not exoplanets, any other transients that might have been caught by this telescope, because it's just looking at the sky all the time. So some of those ones might possibly find afterglows, kilonovae and stuff, but like I said, we're not seeing a ton of them, so we don't have a ton to release to the public just yet, unfortunately. Hopefully, if we have more follow-up and more all-sky surveys, then perhaps that is something that we could share out to the public a bit more.
No other questions? Probably child children. Please come up.
Well, Cassidy, we'd like to thank you very much for coming along to our meeting tonight. It's been fascinating, and it's something that I guess we always appreciate scientists working to help us understand the universe more, and it's great to hear about your work here in Tasmania. So thanks for coming along to our meeting tonight.
Thank you so much for having me.
Okay, well, have a short break and help yourself to some supper and some muffins. Not for you at home, sorry, not our online audience.
Someone was bored this afternoon.
Don't forget to stick around after the break. Have I got a trip across the universe for you as well?
Okay, just quickly, because I know Richard's got some great information on some objects in the sky coming up. So I just wanted to mention to you that in July, and it just really came from a suggestion that was raised at the January meeting where we all got together and throwing around some ideas about having some sort of object, a challenge, etc. We're going to have a Messier galactic bulge challenge in July. So that means the challenge is your own personal challenge. So what it is all about is there are 30 Messier objects, and they're the ones that are in constellations that overlap the galactic bulge. And the objective is, it's a little bit for everyone. So if you're an observer and you use star hopping, you can star hop to the object, each of the objects, do an observation, record your notes, and then go on to the next object. Now, the gold prize is to do all that in one night. And Steve Harvey thinks he can do it. He's probably one of our most experienced observers. He just used a go-to the other night when it was a clear night and quickly wrapped up the 30. So go-to you can use as well. Just slewing across the object, making the notes. And if you're an astro imager, take some images of as many of the 30 as you can, or if just EAA, if you're just observing, record your notes. So there'll be, so you can do the challenge in one night, several nights, take the whole month. There's nothing, there's no really, it's really your own personal challenge to become familiar with some of the great objects in the sky. So there's only 30. We will need to have a few clear nights, I'm sure. Hopefully we will. And if you get a gold star if you do it in one night. We're going to open up a chat channel so that everyone that registers to do the challenge can keep in touch with everyone else. That was one of the things that came out of the January meeting. You wanted to be able to communicate with each other. So we're going to use this as a bit of a trial. And there'll be a resource pack which will be tips and tricks on observing and star hopping. So Steve's preparing that, and that'll be available later in June. There'll be the target list and the data on each of the targets. There'll be a recording sheet and a sky map. So there'll be resources there, also for new astronomers, some support on getting your skills up to be able to do that. So at the end of June, we've got a observing night out at Mount Pleasant, so there'll be people available to help new astronomers get their skills up. So we're hoping that that's a bit of fun for July. And I did refresh my star hopping techniques a few nights ago, and it just reminded me that just doing that, just scanning across the sky, you find some objects that you've never seen before, and it's quite a relaxing process. I don't know about the strain of doing all the objects in one night, but it's your own personal challenge anyway. It's a way of increasing your knowledge.
And there's an observing night this Saturday.
Yep.
So we'll open up at 4 o'clock. There'll be a dark sky. The new moon's actually tonight, so it'll be nice and dark on Saturday.
Yep. So thanks, Dallas. And just a reminder, the freezer jackets giveaway, we've got about 15 or so freezer jackets that are surplus. This Saturday, if you want to come along and grab one, that's great. Otherwise, we'll give them to a charity organisation. The Quattro telescope looks like we might not sell that. We're hoping to sell that this month so that we can fund the purchase of some beginner telescopes. So that'll go on the open market around Australia next month, and hopefully we'll get a good sale there. Just a request, if you have any AST items, anything on our inventory, scopes or equipment, can you return those to Mark Ruff? So he's doing an inventory and we're just checking all the equipment that we have, make sure it's workable. And just a reminder, if you've need any help with your astro equipment, then Mark as equipment officer will be able to help you. The astrophotography group current target is the moon. So Lee set that last week. And the other thing I just should mention is that the open night will be the 4th of July, so the public open night. I've already got 21 volunteers for that, which is terrific. So we're hoping that's a big night for the society. We have the radio astronomy group will be there. There'll be Dark Sky Tasmania. The physics faculty will be there, talking all about, giving information about the physics pathway through the uni. And we have the coffee van, etc. So, you know, we're hoping for another good night. If you would like to volunteer, if you haven't already volunteered, then please contact me. So yeah, thanks. And I think I'll hand over to Richard. So which is timely because he'll be talking about some of those objects that you'll be looking for in July. Yes, Chris?
Just quickly mention, Ross, Roman and I did the Beaker Street thing last Wednesday, I think. It's support for the media encouragement for people to come down and look at stuff, and we were very fortunate. We had a very nice night. It wasn't even overly cold until the wind came up about 9 o'clock when everyone went, but it went over particularly well. Michael was there with us, and that was well received, although I think we had a much luckier night than I think probably Dallas and Beth did. Perhaps you could tell us about your one, Dallas. Was it clouded over? The one that you and Beth did on the weekend. You didn't. So we went up to Pyrmont, overlooking Coles Bay, and we had a great night on Friday night, and saw the Southern Cross and the pointers, but that's about all we saw. So, but the Saturday night was a wipeout, so we just talked to people about black holes and supernova, and everyone had a great time.
Thanks, Dallas and Chris, and thanks for representing the society so well. So without further ado, we'll hand over to Richard.
I've got a microphone. I don't know if this one's working. Can you all hear me? Okay. All right. So, yeah, that's all right. We'll kill the lights, hopefully. I've changed my desktop image to my latest shot of the Blue Dolphin Head Nebula, for those of you who haven't seen it. That's an interesting thing, that that star there has caused, that star there in the middle is EZ Canis Majoris. The one there, oh, is that on or off? Now it's on. The star, oh, you can't see it. Oh, that's great, it disappears on this. I'll have to use this. So, oh look, there's a red dot. This to work so slowly, but the one, that white star is Udra, that's got nothing to do with it. But in the middle there, you can see a little red dot. Yeah, that's the one that's caused that. It's actually an emission nebula and not a reflection nebula. It's very interesting. But anyway, let's get on to the main thing. So you heard Ross say we were going to talk about the battle of the Messier battle, and I'm going to hopefully this will work. Sorry. Are we plugged in? Where's the sound? Oh yeah, we have got some. Gee. Oh, it's too quiet. Yeah, Tchaikovsky. Anyway. So, sorry? No, that's further down. No. Lots of shellfish in that area. No, this is the prawn. Very good, Stefan. So it's the prawn nebula. If you go down here, the next star is Eta Scorpii, then you've got Sargasso, then you've got Girtab, then you've got Mula, and then Shaula and Lasaf, the two there. I couldn't, they're too close together. Now, and the last one down there, that one there, is Fuyue. And you can see it's a little it's like two things, because one of them is a globular cluster. And when the first time I took a photo of that, I thought, what's that next to the star? That's a globular cluster, tiny globular cluster. Now, so if you know where Scorpius is, and you come down here, you can make a few things out. Does anyone know what that is? Very pretty object. You'll be looking at this under the stinger of the Scorpion. You've got two bright objects. I'll put the other one up here, opposite each other. What are they? Does anyone know? So you've got your binoculars out. This is what you need, binoculars. Very good. M6 being? The butterfly. Yeah, there's the butterfly. And wonderful astronomer that whose books we can't get anymore, Robert Burnham, Celestial Handbook. He was the first to describe that as a butterfly in his book, Burnham's Celestial Handbook, volume 1 or 2, I can't remember which one. And that one there is M7, which is Ptolemy's cluster, which was actually spotted by Ptolemy, though he described it as a nebula, like a fuzzy object, in the 2nd century AD. So let's move on. So what other things are down here? Well, look what I'm going to do. Now, what's that nursery rhyme? I'm a little teapot, short and stout. Here is my handle, here is my spout. Okay, here is, sorry for that little interlude, here is what we know as the teapot asterism, but more properly as Sagittarius. So here's the handle. Now, this is easy to see, even though it's hard on this because it's a photograph. These stars stand out easily in a night sky. You can see them any night. Don't need binoculars, telescope or anything. So if you know where they are, you can see things like right there is a very important globular cluster, which you're going to look at, M22. And then over here to the left, you've got this bright patch. Everyone knows what that is. Fantastic through binoculars. Does anyone know? That is the Lagoon Nebula. Lagoon Nebula, mate. Anyway, look, I'll point a few things out to you. Here are some objects. Right next to the lagoon must be the Trifid. Very good. And then over here, M23, which I'll talk about later. Beautiful cluster. And then down here, this interesting object, which I'll photograph partly, is a small Sagittarius star cloud, M24. So we'll look at a couple of these things later. That one's a famous object. Anyone know? Another red gas cloud, a molecular hydrogen, an emission nebula. The Swan or Horseshoe Nebula. And then next to it, moving away from it, back to the globular cluster. I did these in the wrong order. That's M22. What's the next one? The Eagle. Yes, the Eagle, M16. So M17, M16, M20, M8, M20, and down here, M22. So let's move on. There's Serpens Calder I've put on its side because the right-hand side, remember I told you the tail of the snake comes down this side. So it curls up around here is Ophiuchus up here, and the head of the snake comes down this side. So there's Ophiuchus. So there are those constellations. And down here, something special. Sorry? The snake lines. Does anyone know what this lovely little circle of stars is? Corona Australis. Well done, Stefan. Corona Australis. And if you look at it, it's got the beautiful R Corona Australis nebula in it, which we're going to photograph, Lisa. We're going to do that. We're going to get our telescopes out and take a photo of that. It is a beautiful thing. It's got, can you see two dark bits there? It's got two beautiful long streamers. It probably needs a mosaic to do properly, or a wide field telescope. So Corona Australis. Anyway, let's move on. So here we've got these all again. So what I'm going to do is concentrate on this part, Sagittarius. Here are all the Messier objects in Sagittarius. So 15 of the 30 objects you're going to look for are all in this constellation. Now, of course, here's the teapot again, but you can see it spreads out like this. The centaur, its forelegs are around here. This is hitting the sort of chest of the centaur, and up here the centaur is holding an arrow, and that star, Al-Nasl, is like the tip of the arrow. And then down here you've got Nunki and Acela, and they're interesting stars. Actually, it's a lovely area to look at. And there's M22, the one I showed you, the globular cluster. So they're all here. Great Sagittarius cluster in Messier 22. Quite a few. So let's have a look. So there's the teapot one more time. Keep that in your memory. It's turned on its side. So Corona Australis, Sagittarius. Let's have a look now, a little more close-up view. There's the lagoon, M8, and the Triffid. There's a picture I took when I had a camera fail. It was my failure. I hadn't turned the fan on. It wasn't cooling very well, but it did a good job of taking the two in the same frame. Now, down here, Messier 21, another lovely star cluster, open cluster. So these little symbols, you know from stellarium, are open clusters. When you've got a circle like that, it's a globular cluster, and that's the one we just talked about, M22. Lovely thing. Hubble images of these globular clusters are stunning. They're just beautiful. I think better than, well, you can't really compare it to James Webb because James Webb looks at different stuff and it's mid-infrared, whereas we're looking at the optical, just the optical. It's just a pleasure to see those beautiful photographs. AM23, that lovely star cluster, which I'll show you a picture of later. And down here, the Sagittarius star cloud. That's a picture I took near in the Sagittarius star cloud, but that little red bit there. Can you see that? So that's that little red bit. I'll show you that later on. And then, yes, so there is the Horseshoe, Swan, or Omega Nebula. It's got different names. I've never photographed that. Has anyone here photographed the Swan? You have, Lisa? Any success or? Yeah. Oh, right. Good. I'll have to have a look. Yeah. So, yeah. So that's M17. And then further down here, we've got M18, an open cluster, M25, another open cluster, and a very pretty one, as you can see. Gorgeous. Of course, because you're shooting in the core of the galaxy, the background stars are going to be very dominant and pronounced. And so when you take photos, the longer you leave the exposures, the worse they will become, guaranteed. So in a way, it's better to take shorter exposures in this part of the sky because of the background. Right. M28, yes, another globular cluster. Look at them all. They're all everywhere. M54, there's over here, very pretty globular cluster. Most of these are 10 to 12 billion years old. But M22 is actually probably, because of extinction, that is the presence of interstellar gas between the object and us, this would be probably 2 magnitudes brighter than it is. It's also one of the closest globulars, I think. It's only 10,000 light years away or something. I want to say only 10,000 light years away. But yeah, they're all roughly 70, 100 light years, 150. In the case of Omega Centauri, of course, that's a lot bigger. It's about 180 or something light years across. Now, there's a little, I had to guess where that was. There's a nice little star cluster, a globular cluster in there. And there's another one in there, 70. Yeah, very pretty. Anyway, so you're going to have a great time. All you need with all of these things, I'm going to suggest, is a pair of binoculars. I would not use a telescope. If I was doing this to start, I'd get binoculars out. Doesn't matter what binoculars you have, and you will see these objects really clearly because binoculars will take you about 9th magnitude. So you can spot really faint objects with it anyway. And you can certainly see things like the lagoon will blow your mind in a good pair of binoculars. The lagoon is M8, stands out like anything. And the others, even though there's red light and they're fainter, a lot of these nebulae, you can still get them if you've got the right sort of instrument. You don't have to have an expensive optical instrument to see them. So binoculars will show you quite a bit. Even if they're only little faint fuzzies, you'll have an idea of where things are. And I think Steve's going to talk to you about hopping objects later on. So my advice is do that first. Go out one night and just have a look at that part of the sky and see what you can see without having to use a go-to telescope. So looking at the Sagittarius cluster, I've just made up some fields of view. So this is a 7x50 binoculars. So you can see M22 is tiny. I mean, we're talking about image size there. That's a field of view of 6 degrees. So that makes that a few minutes of arc across. It's going to be pretty small. However, if you double the magnification, with my old telescope, which Eugene now has, 30 magnifications, that's a darn sight better than 7. And then finally, if you get up to, I think it's 100, that one, yeah, that's 100 magnifications. So I recommend for star clusters between 30 and 100 magnifications maximum. I wouldn't go above that. Most star clusters will fit into that perfectly, and you can get all sorts of framing, and it's wonderful. Once you get above that, you'll get, well, star clusters are innately bright, well, a lot of them are. You'll get, they'll look fainter and fainter, and they won't look so impressive, and you lose the form, you lose the shape of the cluster, which is much more important, I think, than just looking at stars and resolving individual stars. So, especially with the globular, you can see patterns now, like an S. There's one, I'll come to that. So there's the Sagittarius star cloud, quite big. I think it's about 1.8 or 2 degrees that way, and 1 degree across. So 60 arc minutes across and 90 arc minutes or more, 120 arc minutes that way. So there's that thing I took a picture of. So this is with a Celestron 15 by 70 binoculars. This is the view you get. So you can take in the whole thing in 15 magnifications. So remember what we always do when we observe, we use low magnification. High magnification is useless unless you want to look at, say, Jupiter or something. But I wouldn't look at a lot of these things at high magnification because you get that inverse square law and the thing looks darker, and yes, you get a close-up, but it's faint. There's no point. Sorry, I don't know much about the history of it, Dallas. I couldn't tell you that, but I do like photographs. So here it is again. Now, this shot was taken by a well-known Alan Dyer. You might have heard of Alan Dyer, with a DSLR. And you look up there, and there's the thing I took a picture of, that part of it. So this is pretty much a close-up. And that one up there is a star cluster I mentioned earlier, M23, which is very close to the actual. It's a very pretty cluster, beautiful cluster. I forget what the dimensions of that were. Now, so here we go with my refracted telescope. I put in my Barta 31 eyepiece, so I'm getting exopupil of 4 millimeters. That's good. So if you're old, 4 or 5 millimeters are good. For people like me, 4 or 5 millimeters is a good diameter exopupil from your eyepiece. So a nice bright view, a brilliant eyepiece I can recommend if you can buy one. Cheap, not cheap, medium expensive, but Barta make very good eyepieces, and this is their gold one, which they never talk about, which is ridiculous. Because Steve and I reckon it's a fantastic eyepiece to use for observing. Anyway, so that's a simulated field of view. So there's that thing I took a photo of. Sort of blobby really, but that was a few years ago I took that. But look at these dark areas are fascinating, aren't they? I love them. Adds a bit of character. So essentially a star cloud with IC 1284. 1,000 stars visible in a single field of view, yeah, 2 by 1 degree, 10,000 to 16,000 light years in depth, and about 10,000 light years away, I think, somewhere around that. Now, the lagoon in different views. Here's the lagoon, not Galoon, through 7 by 50 binoculars, so 7 magnifications. Very bright in binoculars, I can tell you, it's amazing. And here we have a view of it at 22 magnifications. So even 20 by 50 binoculars will give you a view approximating that. And the Triffid is in the field of view, as you can see. And that's a much bigger field of view. That's, what's that, 100 magnifications, is it? Or what have I got there? Yeah. Okay, that's with a 10 mil eyepiece, yeah. And my old refractor, which I no longer have, unfortunately. But 70 magnifications is, ample. For something like that, you can see, lovely stellar nursery it is. Now, on to our next constellation, Scorpius. Some interesting objects. Does anyone know what that one is? It's a globular, M4. Now, M4 is Not disappointing. It won't jump out at you, but it's a nice globular cluster to look at anyway through a telescope. That's M4. Now, hopefully, next one. That one is M80, and that's smaller, a smaller globular and not as spectacular. But this area of the sky, of course, we all know this. There's the blue horsehead. Now, M7, Ptolemy's cluster, and M6, the butterfly. So we're going to have a look at those. So there's 4 objects in Scorpius that we can look at. For those who are interested in shellfish, the Prawn Nebula, somewhere in here is the Bug or Butterfly Nebula. The Americans call it the Bug, we call it the Butterfly. Down here you can see the little unmistakable paw prints of the Cat's Paw Nebula, and down here the War and Peace or Lobster Nebula. The way I remember them is there's a cat trying to catch a bug. You know, it's a sort of an order. Anyway, so let's move on. So there's a picture I took only a couple of weeks ago of the Roa Phyke region. Now so this will sort of, what's that there? Roa Phyke, a ficus, so big bright orange star, supergiant star. Antares. We're in Scorpius, so that's Antares. So over here you've got Iota Scorpii, and down here the very famous, this whole thing is named after it, Roa Phyke, which is a quintuplet star, because it's got A and B are in there. There are what do you call them? It's a binary system, but I forget the name of it. I'll come back to it in a minute. It's got a special binary system, and then you've got above it, you've got D and E and C, and there are other stars they think are associated with it too, gravitationally associated with it. So, and down here on the out one, so the front of Scorpius kind of goes that way. So north is down that way, and south is down that way. So if I turned that 90 degrees to the right, you'd know that you were, the Scorpion spread that way. And that little globular is NGC 6144, which is a tiny thing, very small. And this was taken with the astrograph, because you can see gorgeous star spikes. I love star spikes. We all love star spikes. Now, moving on, the butterfly. So there's an old picture the butterfly took with an old refractor. 25 arc minutes. That's not the field of view. That's the width of, which is almost the width of the moon, the butterfly. And you'll love looking at it through a telescope of binoculars. Gorgeous, gorgeous object. So here's a view of it at 50 magnifications, and at, what's that one? How many magnifications? 100. So 100 magnifications will fill your field of view and give you the pattern, a beautiful pattern as described by Robert Burnham. So, all right, I'll speed up a bit. Ptolemy's cluster, this is a Hubble image. Oh, isn't it gorgeous? I have yet to photograph that. This one, the last one, the butterfly, is I think something like 1600 light years away. And this one is 980 light years away, and is a lot brighter, but it's scattered, it's bigger, but still spectacular to look at. 1 degree in 20 minutes, that's quite wide. So in an eyepiece, what's the magnifications there? 30 magnifications or 29 magnifications, you'll get the whole field in there. So we move on. So we've left the Stinger and the 2 star constellations. So we move away from Scorpius and we move to a Ficus, the Serpent Bearer. And just quickly, it has globulars everywhere. There's a Ficus. Now, his legs disappear under the Scorpion. I wonder who drew these things or thought them up. Anyway, it's quite weird. That, by the way, is Hercules, I think, down there. And there's Aquila down there. And there's the stinger of the Scorpion just coming out there. All right, so let's have a look at this area. Up here, there is a very interesting globular cluster, M107. Also known, it's got 10 arc minutes across. It's got called the crucifix cluster, I think, because it's got a crucifix. And I kept looking at it, I blew it up on the wall. I can't see a crucifix. But anyway, in fact, it looks like one of those sea monkeys. It's got arms coming out, you know those sea monkeys. So nobody knows what a sea monkey is, you dissolve it in water and they come to life, and that's the first thing I thought of when I saw that. I know I'm weird, but that's just the thing I thought. Anyway, down here, M12, another. This is worth getting your binoculars and looking around a ficus. So remember, under Scorpius is a ficus, just to the left. And you see plenty of these globulars. These are the arc minute widths of the objects, 16 arc minutes. 20 arc minutes, so we're getting close to 2/3 the size of the moon. M14. So 9, 10, 12, 14, think the ficus. Where are we? Up here, yes. There's 9. That's an approximate area. It's pretty close. 9.3 arc minutes. They're pretty small. Oh, by the way, magnitude-wise, I think, Ross, you're going to distribute your chart of magnitudes, aren't you? Or you're going to distribute your chart with the magnitudes on that? Yeah. Most globulars are, with a couple of exceptions, are around 6.5 or 6.6 to about 7.9 or 8. And then beyond that, much fainter. But we're not looking at the really faint ones. So these are all within your range. And there's M19, 17 arc minutes. And I think one more up there, 62, which is a strange globular because it looks like the head of a comet, and it's got a kind of, looks distorted. And they're very interested in the shape of that and what's going on with that globular cluster. Right. That looks a bit like Omega Centauri, that last one. So now let's go to the objects in Serpens. On the left, on Serpens caput, caput is head, caput, capitis, any Latin, capital, the word capital, head, right? So Serpens head. Sorry, someone said caput. Yes, that's how you would pronounce it actually in the Latin. So the serpent's head. So the serpent's head contains M5. M5 is also known as the rose cluster. Can't see a rose particularly, but anyway. 23 arc minutes. It's a fairly big cluster to look at. I've talked about that before. I'm sure I have, the rose cluster. Now down here is the Eagle Nebula. Now remember the Eagle. Here's that chain of things coming down from Sagittarius. Remember. So you've got all those gas clouds down in a row. So you can always find them. Above it is M17, the Swan Nebula, or Horseshoe, or Omega Nebula, and here is the Eagle. And there's a picture I took using Optolong L Extreme narrowband filter with a lot of hydrogen and alpha light, so that's why it's really red. But up here, you might be able to see the pillars of creation. Can you see them there? Yeah, so that's a lovely object to take photos of. And those of you who've got sea stars and that, you can have a lot of fun with that. And get, with stacking images in real time, you get some wonderful pictures. Very big. In fact, I think 70 by 50, but I think it's about 120 light years across. So it's quite a substantial molecular cloud. Now, what have we got here? Oh, yes, that's right, scutum. Now, scutum's shield. And in the middle of the shield is M26, a pretty little cluster, nice to photograph. I think that's by a guy called, Joseph Drudas. He's got some wonderful images if you look him up. He's a really good photographer, and he does a better job than a lot of professional photographers, I think, or people who've been imaging for years. He just seems to do star clusters really well. Nicely exposed, very, very nice picture of it. Anyway, so that's 14 arc seconds. And then over here, M11, the wild duck cluster. Now, if you look at this, can you see a duck? Well, if you look this way, it's got a wing there and a wing that way, and its head is down here. neck, and the head. No? Well, so some people say it's a whole lot of ducks flying in formation, but I prefer to see one. I see one duck. Anyway, 23 Archimedes. Now, that is a gorgeous cluster and worth looking at, gawking at for a while. So, finally, penultimate slide. Here is the Messier chart. You can get this online. It's free to download if you ever need to know all the Messier objects. I think when Messier died, they were up to, I think he got to 100, 9900, and of course he didn't know they were galaxies. So, but after that, these were all added. So the ones after that are definitely additions in modern times. But it's interesting from my point of view to see this is almost like a time chart, because as you get along here, the really fuzzy things are galaxies, and they didn't have the optical instruments to see what a galaxy really was. So you know, that's why the latter ones are more galaxies rather than anything else. So when you look at the crummy mirrors they had, I mean, what would Newton do for a telescope today? The telescopes we've got, the ones we just take for granted when we're taking photos. Wow. Curly's toes. Now, last slide. So I thought to myself, after you've completed the Messier galactic bulge, you need a stiff drink, and there is only one drink in the universe that would do the trick. And listen to the bubbling, because that is Farlean marsh gas coming out of the drink. There's a recipe for this online. I love that, the Pangalactic Gargle Blaster. I love that whole series of books, actually. Yeah, Slarty Bart Fast. Oh, the names, just wonderful. Anyway, if you haven't read The Hitchhiker's Guide to the Galaxy, get it. It's just a good laugh. And that's it, folks. Sorry for the quick tour.
Thanks very much, Richard. I hope that's working out the top for the
Oh.
challenge. It's a great way of finding some new objects. So we're going to get the list. In June, you'll get the pack. So thanks, Lisa. In June, you'll get the pack of all the information, the list, the tips, and we may be able to get a PDF of Richard's presentation here, just so you can refer back to. It's got a wealth of information. Yep.
Yeah.
Is that possible?
I could do it again if people wanted a reminder, or I can.
Yeah. Okay.
No problems.
Beauty. And thanks, Cassidy, for staying and your presentation. Yeah. Thank you again. We really enjoyed that. And also, look, big thanks to Matt, who comes down from Oatlands to open up for us every month. So thanks very much, Matt, for what you do.
Yeah.
And a very special thank you to Lisa. I mean, amazing job tonight to get through the technology and make it work and happen for us. So thank you very much.
And also we should add, we have in our midst a superstar in Dallas who managed to squeeze through the library doors and we couldn't open them. He was so thin. He was the only person who could get through so that we could disarm the library, because it was the books had jammed the doors. All the returns at Easter had piled up. Looked like Mount Vesuvius there. It was unbelievable.
Yeah, we had 5 days to return the book.
Yeah, and we couldn't get in. And we couldn't disarm the library, and we rang people, and then finally we and and he managed to get through. I still can't get over it. It was a tiny crack like this. Physically impossible. Yeah. Anyway, great. All right.